today we'll get into FETs. We'll introduce the topic of FETs. FETs stand for field effect transistors. As part of your syllabus, FETs is a small component. Most of the rest of the quarter will be looking at BJTs, bipolar junction transistors. Okay, but FETs, we have a lab on FETs, so I always want to do a little bit of theory behind field effect transistors and a little bit of JFETs and MOSFETs. So let's look at our, that's not, okay. So FET stands for field effect transistors. Was the earliest demonstration of the field effect, or actually the theory that was postulated was in the in the mid 50s, around 1954, 1955. But a working prototype device was not presented much later. And then from FETs, we had, MOSFETs. Let's go here. So we have three different kinds of FETs: JFETs, junction FET, MOSFET, metal oxide semiconductor FET, and MESFET, metal semiconductor. We will start with the JFET. So we look at a little bit of the JFET construction, some equations governing its operation, and then a little bit of the MOSFET. MOSFETs, when they were first presented, were not easy to manufacture. They had very high power dissipation. And so as a functional device, it took a while for it to catch on. But once they were able to create MOSFETs with reasonable power dissipation limits and a easier fabrication process, they quickly took over and have now become the de facto choice for all integrated circuit devices. So this is now the most popular choice of creating electrical or electronic circuits. Okay. Your 307 course, which you will take in the next quarter, is all about MOSFETs circuits. Okay, so you will study this in depth for the entire quarter. You'll create digital logic circuits using MOSFETs. Okay, so let's look at what a JFET looks like. So here is a top level or a top view of a typical JFET transistor. JFET is a three-terminal device. The terminals are labeled as gate, drain, and source. Okay, gate, drain, and source. So typical construction would look like this. You'd have a silicon wafer. Okay. Silicon wafer with some intrinsic concentration. And then we would implant either a N-type, we would create either a N-type or P-type structure inside our silicon wafers. So let's see if it looks something like this. If this structure is N-type, then it's known as an N-channel JFET. If the structure is created from P-type, then it's referred to as a P-channel JFET. Okay, so for purposes of explanation, we'll say that this is N-channel. Excuse me, N-type material. Okay, N-type material. And then inside this N-type material, we will create we will implant two junctions of P-type material. Okay, so we implanted two separate areas with P-type implants. And what this does is it creates a channel inside that N-type material. The two farther ends, or the two far ends of this N-type material are labeled drain and source. Theoretically, we could create this as a completely symmetrical device. So the drain and source can be interchanged. Okay, the drain and source can be interchanged theoretically. And so there is a narrow channel between that connects the drain and the source, and hence the name N channel or P channel FET. The P-type materials are connected together. And they're labeled as a single terminal gate. So there is a gate, there is a drain, and a source. And as the name suggests, that's what the device is. You have a source, you have a drain, and there is a gate that controls the flow of water from the source to the drain. In this case, it's not fluid, of course. In this case, it's electrons. So the movement of electrons, which constitute the flow of current, is controlled by the externally applied voltage at the gate. And that's, in short, the operational principle of the FET or the JFET. Okay, let's take a 10-second pause. Let me know if you have any questions regarding the construction. Any questions? So far, so good? Yes. So it's not between the two P regions. The two P regions are connected together internally. And so they're connected internally together, and it's one single terminal. So they are basically just shorted together. So now the device is being shown as at equilibrium. So think back to chapter 2. We had a PN junction, and the PN junction at thermal equilibrium, what did we have? We have a depletion region. So there are two PN junctions in this device. We have an N-type channel, and you create P-type material or implant P-type material on either end, on both sides of the channel, that creates two PN junctions. So there are two depletion regions that is completely devoid of charge carriers. Does that make sense to everyone? Right? So there are two PN junctions in there. And then this is what happens. Actually, let's wait and finish up the symbols. So these here are the symbols of the JFET. You have the drain, the source, and the gate. The gate has an arrow. If the arrow points inside or internal to the device, going into the device, then it's the N channel. If the arrow is flowing out of the device, then it's P channel. Right there. Now, typically, you might see something like this. The arrow is in the center, not towards one end, not towards the drain or the source. But both conventions are still valid. Okay, both conventions are still valid. So this here shows a device where we have connected VGS, meaning the gate to source voltage is 0 volts, and the drain to source voltage is also 0 volts, meaning there is no externally applied voltage between the drain and the source. Okay, between the drain and the source. In order for electrons to move or flow, an externally applied electric field must be present. In this case, device is at equilibrium. There is no externally applied voltage. Drain and source are connected to ground. And then the gate, which should control the flow of electrons, is also connected to ground, connected to 0. This is at equilibrium. Okay, at equilibrium, you have a depletion region on both sides of the channel, and the channel has length as well as it has certain width. Okay, that is equilibrium. Now, VGS means you are applying positive reference, or you're measuring VGS with positive reference at the gate, negative at the source. So if VGS goes below 0, VGS goes below 0, meaning you are applying a negative voltage, meaning the gate, which is P-type, is lower than the source, which is N-type. The junction is reverse bias. When the junction is reverse bias, what happens to the depletion region? It increases, as shown right here. So reverse bias junction and depletion region increases. The depletion region increases, the channel narrows, the channel width decreases. If you crank up, or actually crank down VGS, meaning you increase the reverse bias voltage between the gate and the source, the depletion region increases so much that at a certain point, both depletion regions will end up meeting somewhere near the middle, thus pinching off the flow of electrons, or pinching off or cutting off the channel completely. And that point is known as a pinched off channel, and that voltage is known as the pinch off voltage, VP. And we say the device has no current flow and is completely turned off. So device turns off. Okay. Before any sort of voltage is applied, the channel is open. If the channel closes, then we say device is turned off. That point is also known as the pinch off, and the voltage that is required to pinch off the channel is known as the pinch off voltage. Okay, pinch off voltage. All right, let's take a pause. Let me know if you have any questions. So far, so good. Okay. Now, when I said the device turns off, well, the normal state of the device means the device is always on. Okay. But when we say that a device is on, means in the state, the channel is open, so it's in a state of readiness. So if VDS is not equal to 0, there would automatically be a current flow. The gate is not controlling anything, hence the term that the device is always on. A negative voltage must be applied at the gate to turn the device off. Okay, so the device is inherently said to be turned on all the time. And hence, since a voltage needs to be applied to turn the device off, it is also known as a depletion mode device. Okay, it is known as a depletion mode device. So normal state is on, hence depletion mode device. So it's always in a state of readiness. If VGS is 0 and VDS is 0, if VGS remains 0 and you increase VDS, you will have current flow. We don't have to do anything else. We actually have to apply an external voltage to actually turn it off. So the device is always on. In which we'll see in the next slide. So right here, VGS is kept at 0, VDS is at 0. Then you simply, not simply, when we slowly apply VDS greater than 0. Okay, VDS greater than 0. So the drain to source is now positive. What happens? You have a large number of free electrons available in the n-type material, and you're applying a positive voltage at the drain. So electrons are now propelled towards the drain. So current is now flowing in the opposite direction. Okay, so electrons are coming this way. And of course, current is flowing in the opposite direction. So you have current flow. Now, for every applied voltage of VDS, if you wish to turn the device off, you have to keep increasing the reverse bias at VGS, meaning we have to apply an increasingly negative voltage at VGS to turn the device off. Okay. So you can see here, VDS positive applied, and then VGS kept to 0. But for every level of VDS that we apply, there is a separate pinch-off voltage. All right, any questions? Yes. Yes. So this is pinch off. And so is this. Both of them are pinched off. Okay. Now the reason for this angle depletion region is because of fabrication. It's fabricated such that the number of accept atoms is a lot higher than the number of donor atoms. Na is much, much larger than Nd. So there's a whole lot more positive charges available than the negative charges in the n-type region. Okay. All right, questions? All right, then I'm going to end class here today. This is where we ended for the earlier section also. So I want to keep both sections in sync. And so we'll end a few minutes early today. And then we'll pick up here again on Wednesday. All right, I'll be available all day today until 5 p.m. in my office. So if students have questions, feel free to stop by. Yes.
I want to go to the last place.
What happened with the last quiz?
Or I want to go over the last quiz.
Okay.
The 4.
Our work or the study?
Are there?
Yeah. You haven't checked? You will not check? Maybe I should post an announcement for that. Oh, typically.
So wait, I'll review the solution first.
Okay. Realize. Hey, how many of you have, I just realized I should have posted an announcement, but the quiz solutions have been posted regularly. So have you been checking those or not? So I guess it's on me. I should have informed students. I just assume the students will be checking, so. So the solutions are on there on the website. Sorry, what's
the first one?
No, no. Yes.
Are you uploading the Friday's video? Cause I didn't see, I
Sorry,
wanted,
there's
I didn't see the Friday's video on.
video,
In both, either playlist.
latest?
Yeah,
It should be there.
'cause the earliest one in both of them was from the multiple diodes.
Let's see. No.
Was it there? Was it at the bottom? Okay. I didn't see, I thought the.
I don't know how it shows up. I think it's just arranged by date or something. I guess at the viewer's end, you can arrange it, but it's, yeah, it was uploaded.
Okay, I guess it's at the bottom. I just like saw it at the, I didn't see it at the top. Okay.
Does it usually come at the top?
Yeah, it normally comes at the top.
Just, I would say, the channel is not monetized. I mean, it's free for all.
Yeah.
I don't make any money off of that, so if you want, go ahead and subscribe to it, so it sends you a notification every time it's done. Typically, I upload it right after class, but if I have like meetings or something going on, then there might be a delay. But other than that, it's always posted.